Regents exam, Algebra 1, August 2016, problem number 25. Graph the function y equals negative square root of x plus 3 on the set of axes below. In this problem, we are provided with the equation of a function along with a coordinate axis. We are asked to graph the function on the axis. We can accomplish this by setting up a table and generating a series of points by choosing appropriate values of x. These values represent the x-coordinate of the point. We then evaluate the function with these values to obtain the output or y-coordinate of the point. In the end, we connect the points with a curve. Notice that the function represents a radical function, particularly a square root function. Remember that the domain of square root functions are restricted to real numbers that make up the radicand, the variable expression inside the square root, greater than or equal to 0. So let's first determine the domain of the function by setting the radicand equal to or greater than 0 and solving for the variable x. Solving the inequality, we obtain x is greater than or equal to negative 3. This means that we should use values of x that are greater than or equal to negative 3. Typically, it is best to choose values of x that allow us to take the square root of perfect squares, like 1, 4, 9, 16, 25, and so on. This way, we can evaluate the function with relative ease. For this problem, let's evaluate the function at x equals negative 3, negative 2, positive 1, and positive 6. If we had more room, we could also evaluate the function at x equals 13, but the first 4 values are more than enough. Evaluating the function at these values, we obtain the following outputs. Now it is just a matter of plotting these points. Doing that, we obtain the following. The last step is to connect these points with a curve, as follows. Making sure we include an arrow on the right side of the function, indicating that the function continues in that direction beyond the plotted points. Notice that the leftmost endpoint of the function is a closed circle, since the domain of the function is restricted to values of x that are greater than or equal to negative 3. So we should not have any points plotted to the left of negative 3, nor should we have an arrow pointing to the left of negative 3. An alternative way of graphing the function is to make use of transformations. Recall that a parent function can be used to graph a transformed function. In general, a function can be translated up or down by adding or subtracting a constant to the original or parent function. In the same manner, a function can be translated left or right by subtracting or adding a constant inside the argument of the function. We can also flip the function across the x-axis by multiplying the original function by negative 1. In this problem, the parent function would be the function y equals the square root of x. This function represents an original untransformed function. Let's go ahead and graph this function by using the values of x that allow us to take the square root of perfect squares. In this case, we choose x equals 0, positive 1, positive 4, and positive 9. Next, we go ahead and start applying transformations. Notice that the given function has the quantity x plus 3 in the radicand. So this transformation is going to be a translation to the left of 3 units. Remember, transformations inside the argument of a function behave in the opposite way when compared to transformations that are applied outside of the argument. So we take every single point of the parent function and shift them to the left 3 units. Doing that, we obtain the following graph. The last step is to apply the transformation associated with a negative sign. This transformation will flip the graph about the x-axis. This transformation works by multiplying each y-coordinate of the function by negative 1. Doing that, we obtain the following graph. Notice that we obtain the same transformed graph. So either method will work. You can start from the parent function and apply transformations, or you can make a table and generate the points by evaluating the function at particular values of x. So this graph is our final answer.